I'm Adam, and I'm with George, Fernando, and Sarah, and we're going to be discussing Facebook AI's object detection paper using transformers, known as DETR. So this is just an overview of how our presentation format's going to go. I'm going to cover the introduction, some related works. George is going to cover the model. And Fernando and Sarah are going to split the experimentation results. They're pretty dense. So Fernando's going to do the object detection and Sarah's going to do the segmentation. So DETR directly predicts bounding boxes of detected objects, which means they don't have to go through some of the additional steps that other object detection models have to go through, like anchor generation or non-max suppression. One of the important components that allows us to do this is their set-based global loss, which they use a bipartite matching loss to ensure that they have a unique prediction for every ground truth label. And of course, the transformer architecture is a major component because of the global computations that they perform in their global view. This helps with removing duplicate object detection predictions. And it also allows the bounding boxes to be quite large so that they can detect large objects. However, as we'll see later in the results, it doesn't do as well with detecting smaller objects. But so really quickly, I'm just going to go over a brief overview of the model. And I want to first point out that there are two things to look out for in this model overview besides the transformer, and that is the set of box predictions and the bipartite matching loss. So just keep these in mind as I go over this. Our input is just a regular RGB image, and it's going to be input to a CNN with a removed classification layer. And so the output of that is a set of image features that we're going to change the dimensionality so that it can be input to this transformer here. So the output of our transformer is this set of box predictions that contain a class and the box coordinates. And this class can be any of the classes that it's seen in training, as well as this no object class. And this is important because since the number of box predictions is fixed, the idea is that we want to have more box predictions than we have items in our image. That way we can achieve a direct set match for each prediction and ground truth label. And then for the bounding box, they use normalized center coordinates. So we have this center X, center Y kind of 2D coordinate here in the middle, and then we have a height and width, and this is how we get the bounding box. And once we have these, we perform a bipartite matching loss. So the idea is that each match has a cost value associated with it. And our goal is to derive a set of these matches such that our cost is minimized or our loss is minimized. And quickly, I'm going to just go over some related works. I'll cover a little bit of previous object detection methods. I'll cover the bipartite matching and how it's achieved. And of course, this is based on a transformer. This is kind of just a reference. So typical object detection methods use some form of post-processing, like non-max suppression, right? So just as an example, if our model detects this 3 instances of the same truck, we might perform an intersection over union where we calculate the intersection of our prediction with the ground truth label over the union of the prediction and ground truth label. And the idea is that we'll keep the maximum value that we get from calculating those, and we'll suppress the rest. But of course, this is done as a post-process step, right? So with bipartite matching, no post-processing is required. And the way we achieve this is using this Hungarian method. And the idea is to just find the least cost assignment for a square matrix, right? So just as an example, let's say we have these three predictions and we have three ground truth labels. This might be our matrix, right? And so we have these kind of these values here represent like the cost for each one of these matches that we might choose. And so the way we can find the least cost is the first step would be to look at each of these rows and take the minimum value and subtract it from all the values in that same row, right? So I'll take this 2,500, subtract it from 4,000 and 3,500, and I'll do the same with this guy and this guy. And then our matrix will look something like this. And then we'll do the same thing column-wise. So we're going to take this 0, subtract it from these guys, this 1,500 from these guys, and this 0 from these guys. And you'll see this is what our resulting matrix looks like. We want to use these zeros because these are now our representative like least cost matches. One quick thing to note here is if we were to choose this this match here, this prediction 0 with ground truth 0, we would no longer have this ideal match here, P2 to G0, right? So this is not one we want to choose. But another way we can tell we're done is if we're able to cross out the zeros with a minimum number of lines, such that the number of lines matches the amount of matches we need. That might have sounded a little complicated, but we can cross out these zeros with 3 lines, right? And this kind of represents we have 3 matches here. There is a scenario that I'll cover really briefly where that's not the case, right? So this is a slightly different matrix, but we do the same operations. And this is our resulting matrix, right? We did the horizontal and vertical calculations, but now we can cross out all the zeros with just 2 lines, right? So we're not done. We need a third line essentially. And the way we can achieve this is by taking the lowest value of an uncovered row. So these rows are not covered here, these top 2, and we're going to take the lowest value, which is 500. And then we're going to subtract it from the uncovered rows, right? So we're going to subtract 500 from this row and 500 from this row. And this is kind of what it looks like. So you'll see we have -500, 0, 2,000, etc. Right? And then we're going to take that same value, this 500, and we're going to add it back to the covered column, this guy. And this is our resulting matrix. And you can see now we're not able to cover the zeros with less than 3 lines. So this is how we know we've achieved our end goal here, right? And you can see these green squares are what our set of matches would be. So that's how we achieve bipartite matching using the Hungarian algorithm. And then, of course, this is mostly just reference. We've been over this a lot of times. George is going to cover a more advanced or detailed version of their transformer model. So I'm going to hand that over to George right now.
Oh, sorry, can you hear me?
Yes.
Yes.
Okay, can you see my screen?
Yes.
Okay. So hi, I'm George, and I'll be covering the model's architecture along with its loss function. So this is an overview of the model. Over here, we first start off with a ResNet CNN, which produces a set of image tokens, image features. We then add some positional information to these features to tokenize them, to feed them through this transformer encoder. We then feed this output of the encoder into the decoder along with a set of object queries. So what are these object queries that they're passing in? So this diagram shows where this specific one object query is looking, and it's predicting the center of the bounding box within an image. So each dot corresponds with the center of a bounding box, and the color of each dot corresponds with the size of the bounding box. So a green a green color would represent it's a small bounding box, purple would mean it's medium, and red would means it's a large bounding box. And this means that wherever the dots are for this specific object query, it pays attention to that region within the image. So this specific object query would pay attention to small objects on the left-hand side of the image. So an example of this is that for this specific object query, it would likely check small objects in the bottom left. So this baseball in the bottom left could be a potential output for this specific query. So this diagram shows 20 object queries out of the 100 they had in the paper and where their predicted bounding box centers ended up along with their colors. As you can see, each of these object queries pay attention to a different region. Like we said, this one pays attention to the left side, while this one could pay attention to the right side. The weights of these object queries are randomly initialized at start, and they learn to look at different sections of the different regions inside a image due to the bipartite loss. This ensures that no two queries try to predict the same object, since the goal is to remove non-maximum suppression. We can achieve this by adding an extra class representing the no object. So extra object queries could predict the no class and there would be no overlap. One downside of this approach is that if an image were to have more than 100 objects in it, the detour model wouldn't be able to predict all of the 100 objects since it only has 100 object queries. Another downside of this is that since these object queries were randomly initialized at the start, this leaves room for improvement because it requires more training epochs to train these object queries on where to look. And we'll see in a later section, in a later presentation in the detour paper, how they address these issues. So after we pass these, the output from the encoder and these object queries into the decoder, it predicts a set of object query features. We pass these object query features into a feed-forward neural network, which acts as a classification head in predicting the class, along with the bounding box. And all of these feed-forward networks are the same network. So now I'll talk about the loss function. So this is the loss function they use. The prediction they're trying to predict contains the class and the bounding box. And what they do is they take the cross entropy between the class and the truth. They take the cross entropy between the classes, and they take the mean squared error between the bounding boxes, as long as the class itself is not the none class. And then they add these two losses together to compute the class. And what they do is they compute the loss between every prediction and every ground truth to produce the 2D matrix. And then we use the Hungarian method that Adam mentioned at the start to get the best matches between the predictions and the ground truths. And now I'll hand it over to Fernando to cover the experimentation section.
All right. You can see my screen, right?
Yeah, we can see it.
You can see it? Okay, just making sure. Just a quick overview. First, I'll go over object detection experiments that they performed. Then I'll talk about the set of small ablations experiments, including varying the number of encoder layers, varying the number of decoder layers, removing the feed-forward network, passing the positional encoding once at decoder input versus adding the queries at the decoder attention layer, generalization to an unseen number of instances, and finally, they extended their model to perform panoptic segmentation. I'm going to introduce the 4 different versions of DETR models that the paper uses in the experimentation section. The blue row is using the ResNet 50 as a backbone, while the orange is using ResNet 101. The unmodified column is using the vanilla implementation of DETR, while the dilated C5 stage increased the feature resolution by adding a dilation to the last stage of the backbone and remove a stride from the first convolution of this stage. These models were marked with a DC5, as you can see in their names. They used the COCO 2017 dataset, which contains bounding boxes and segmentation annotation with an average of seven instances per image up to 63. Just as a quick recap, you may recall the famous intersection over union metric, which is simply the area overlap over the area of union. Here's a quick visualization of how different intersections over union scores look like. In general, the lower it is, the looser the detection, while the higher the score, the tighter it is, meaning 0.9 is great. Then we have precision, which is just the number of true positives over the sum of true positives and false positives. For object detection, though, we can look at the intersection over union score and do a cutoff to have everything below marked as a false positive and everything above as a true positive. Then we have recall, which is almost the same thing, but we divide by the sum of the true positives and the false negatives. And finally, this is what I've been trying to build up to, the average precision. If we plot the recall in the x-axis and precision in the y-axis, then the area under the curve will be the average precision. However, we have a few forms of AP. We have AP50 and AP75, which refer strictly to a threshold of 0.5 and 0.75 respectively, while AP alone refers to 0.5, 0.05, 0.95, meaning it goes from mediocre detection to perfection. And the AP with a small s, m, and l, meaning small, medium, and large objects. For the exact size, we can look at this as a reference in case someone has any questions regarding that. Things to note here, though. First, the blue corresponds to a backbone of ResNet 50, and the orange represents ResNet 101. And here we are comparing faster RCNN versus DETR, the four models that I introduced earlier. I want to direct your attention to the arrows under the gigaflops per frames per second. Note that while the blue gigaflops have similar values, the frames per second is less than half of the DTR. And the same story happens with ResNet 101, the red one. This may be explained by how the CNNs are already so optimized in the hardware level that transformers might be on a disadvantage in this comparison. But if transformers can't overcome this in the future, then these results are even less impressive, since DTR is basically running twice as long currently. Next, we have the average precision columns. For the AP results, note that DTR has slightly better AP than faster RCNN for loose detection, and it really struggles with tight detection. And if we see the rest of the columns with AP small, medium, and large, we can see how it performed very bad with small objects. One factor for that could be that they use dropout during training by removing random crops of the images to improve the global relationship learning. Another thing I want to point out before leaving this slide is that for large objects, it performs significantly better, even vanilla DETR. This is, in my opinion, the most important part of this table and what we can take away from this result. Next, the authors vary the number of encoder layers and found out that the more encoder layers they use, the better the AP. But the most significant jump in performance were from non-encoder layers to one layer, and even a greater jump if looking only at the AP on large objects. Here is a nice image of the encoder output visualized. Here they took a query token from the output and then append all the keys vectors of the image. We can see how the encoder is already separating instances that can be later extended to image segmentation. For the next experiment, the author varied the number of decoder layers to show how the Hungarian loss removes the need for non-max suppression algorithm. Here the x-axis is the decoder layer from which we will measure the output, and we can see how applying non-max suppression algorithm only matters in the first layer, but as we go deeper in the network, the Hungarian loss is really showing its benefits by bringing up the AP up to the same level as if we were using non-max suppression algorithm. Moving on, here's another example where they grab this image of a giraffe and basically copy-paste it multiple times to create a synthetic image, which with more giraffe that it ever saw during training. And again, this is the fake image with the copy-paste giraffe from previous slide. They did this to show that DTR is able to generalize to a greater number of instances of objects, and this specific sample performed really well with a detection over 93% for all of the giraffes. And similarly to the encoder, we have the decoder attention visualization, where the attention for each object instance seems to be focusing on the extremities of the object. You can see, probably to help facilitate the calculation of the bounding box, but still get enough to classify it. Here, again, you can see each color instance is focusing on extremities. Even the orange zebra, you can see on the bottom left foot, it was able to classify it. Classify it, but I'm not completely sure why the bounding box is not surrounding it. They didn't really address it on the paper. But anyway, now Sarah will go over the last and final topic, panoptic segmentation.
Okay, so to prove that DETR is capable of image segmentation, the authors added a masked head on top of the decoder outputs to do panoptic segmentation. After training the model to do object detection, they froze all the weights and trained the masked head. The input to this model are these box embeddings, which is the output of the decoder, and these come from the output of the DETR model. Then it uses multi-head attention model with M heads to generate attention heat maps for each of these objects. This FPN style CNN increases the resolution and makes a final prediction. The masked head then uses a pixel-wise argmax on the mask scores to assign the mask scores a category. This entire process never results in overlaps for the final masks because of the argmasks. As a quick recap, PQ is the panoptic quality, which is divided into segmentation quality, SQ, and this is how well the model will segment objects like the cow in the previous slide by getting the pixels correct, and recognition quality, which is how correct the labels of a segmented object are, like labeling the segmented cow a cow. And this is an example that shows the difference between segmentation quality and recognition quality. The left image is the ground truth, and the right is a prediction by the model. We can see that a model missegmented 2 out of 3 people because it labeled these 2 people as one person. And so that hurts the segmentation quality of a model. And a model misrecognized the dog as a person, which hurts its recognition quality. So this next table will use these metrics. The panoptic qualities with the TH superscript is regarding the things categories only. Things are usually smaller objects like the person and dog that we saw in the previous slide. Similarly, the panoptic qualities with the ST superscript is regarding the stuff categories only. Stuff are larger objects like the grass and sky from the previous slide. Again, we have the same color scheme as previously, where everything in blue is the ResNet 50 backbone and in red is the ResNet 101 backbone. And in this table, we can see how the DC5 DETR models are dominating in panoptic segmentation. They're getting the high scores, but DETR struggles the most with the segmentation of things and objects. This is probably because it also struggles with detecting small objects. So we can see that it's no longer getting the high scores. Instead, this panoptic FPM++ is getting the best scores on these things, panoptic qualities. However, DETR excels on the segmentation of the stuff and background. This is probably because these are typically large objects, and the global reasoning given by the encoder attention probably plays a big role in this. An interesting thing to note is this purple box, the DETR DC5 with the ResNet 50 backbone outperforms the DETR DC5 with the ResNet 101 backbone. Even though the ResNet 101 has more parameters, this might be because of overfitting on the model. So this is an example of the output, and we can see that it did a pretty good job. All the pixels are labeled pretty much correctly, except it thought that this dishwasher was part of the cabinets. This is another example of the output of the panoptic segmentation. These are all with the ResNet 101 backbone, by the way. This bus model is somewhat well segmented, but there's separate buses back here, and it thought that it was one bus, and the other things are well segmented as well in this image as well. And this image had the best segmentation that the author showed. The giraffe is segmented correctly along with the sky, tree, and grass. In conclusion, the most important components are the global self-attention and the encoder. And from the ablation study, we know that the number of encoder layers, even one, made a significant improvement. The number of decoder layers, the more the better up to a certain point. The feed-forward network, removing it might decrease the number of parameters, but the accuracy will suffer. Positional encodings, these are required and cannot be removed. And the Hungarian loss is also important because it removes the need for non-mex suppression. All of these things significantly contribute to the final object detection performance, and they also create a model that is able to be extended into panoptic segmentation as well. And here's our references.